Welcome back to ChemDoctor, and this video goes out to Tanner D, who's studying chemistry like mad up there at NAU, and all you other new college students who are in first semester general chem for the spring semester. And this video is going to focus on the isotope. There will have to be a series of videos here because to adequately cover this whole situation, I can't do it in just one. So we'll start with the basic definition here. An isotope, this is an atom with a different number of neutrons. So what does that mean exactly? All right, so we learned flat out first thing in chemistry that the atoms of a particular element all have the same properties. And then all of a sudden creeps up this issue of the isotope, and suddenly you wonder what's going on here. Because the truth of the matter is that the atoms of all one type of element don't have all the same properties. The main thing being that there are subtle differences in mass, all right? And where this happens is with the concept isotope. So let's start by talking about there's actually 3 isotopes of carbon, but we're going to pretend that there are only 2 for the sake of this discussion. All right, and one of them is going to be C12 and the other one's going to be C13. So we're going to assume that there are only 2 isotopes of carbon. And the atomic mass of the C12 is 12.0000, and the atomic mass of C13 is 13.0034. And then there's this thing called natural abundance. All right, and the fractional abundance of the C12 is 98.93%, and the fractional abundance of the C13 is 1.07%. All right, now what does this mean? So, okay, if you imagine that carbon atoms could talk, if you can imagine that they could walk and talk like humans, and you randomly invited 12 of them to come into a room, or excuse me, if you randomly invited 100 carbon atoms to come into a room, all right, and then sit down so that they were evenly dispersed around the room, what the fractional abundance means is that about 99 of those atoms are going to be C12, and about 1 of those atoms is going to be a C13. The difference being is that the C12s all have essentially 6 neutrons, whereas the C13, the one individual out of the 100 individuals in the room, has 7 neutrons instead. How do I know this? All right, this number at the top on the left side. So this notation that we're using here, where we have the atomic symbol, and then you see that there are 2 numbers. One number is up and left, one number is down and right. The number that is in the upper left, all right, is what we call a mass number. All right, and the mass number is literally the number of protons that are in this particular isotope plus the number of neutrons. All right, and so you can determine the number of neutrons easily in this notation by literally just taking the difference between the mass number and then the number which is in the lower left-hand corner, which is the atomic number. All right, so the atomic number, hopefully you'll remember from the beginning of your classes, is equal to the number of the protons. All right, so using this notation, which happens to be called the AZE notation, but utilizing this notation, this lower number on the left tells you the number of the protons. The number in the upper left-hand corner defines the sum of the protons plus the neutrons. So you can very easily determine the number of neutrons in a particular isotope. So this isotope has 7 neutrons. This isotope has 6 neutrons. Okay, now, so going back to the room, just to reiterate, all of your isotopes, so I'm going fast here. So if we were to dig a chunk of carbon out of the mantle of the Earth, all right, crush it up into a really fine powder, and then take the powder and continue to crush it up until we could separate, literally, we could spread that powder out onto the surface of a table so that we literally had individual atoms on the table, and then we would draw a box around 100 of the atoms. In the situation of carbon, about 99 of those atoms are going to be C12, and about one of those atoms out of every 100 are going to be C13. Now, how do we figure out the atomic mass from that mixture of atoms? Because for chemists, when we're carrying out chemical reactions and things like that, we're going to need a way of being able to find the average mass of these atoms, and it's got to be in a situation that's convenient. So what we're going to do to figure out the atomic mass of carbon is we're going to calculate what's called a weighted average. So I'm going to write that down. We're going to find a weighted average. And the way this is going to work is we're going to calculate the average mass by summing together the isotopes and compensating each of those isotopes for their fractional abundance. So the easiest, probably the easiest thing to do here is to show you how this works. So we'll start with the carbon. We're going to have, in terms of the first isotope here, it will be the one that has an atomic mass, and this atomic mass is in units of what we call AMUs, atomic mass units. And I will talk more about this in subsequent videos. For now, just accept the fact that this is an atomic mass unit. It happens to be representing the carbon-12 atoms, and then we're going to multiply this times its fractional percentage. So that's this number here divided by 100, so it'll be 0.9893. This is a weighted average, so we're going to add this to the atomic mass of the C13 isotope compensated for its fractional abundance, which is going to be 0.0107. So we took its percentage, its literal percentage, and divided by 100. Now, and we add all of this up, and what we get is 12.01. This 12.01 AMUs, and this is the atomic mass of carbon. Atomic mass of carbon, if you look on the periodic table, all right, underneath the symbol, you will see its atomic mass is 12.01. All right, and above the symbol, usually you see the atomic number. So now you know where this number comes from. All right, this is the weighted average, and you'll see a weighted average underneath all the symbols on the periodic table. Similar calculations were utilized to figure out the average atomic masses for all of the elements that are on the periodic table. And with that, I'm going to go ahead and close this video.